Okay, today I'm going to talk about Greens theory. Okay, before I discuss Greens theory and its application, I'm going to go over line integrals. Right, when we talk about curve C, we usually means curve with an orientation. Okay, so and it actually is orbit. Then which is going to be parameterized by the vector function. Okay, now if I change the orientation, okay, so C, we put negative sign here. That means it's the same curve orbit, but the orientation is changed. Okay, so this is so if you have to parameterize, you can, if here is t is between 0 and 1, then I can use another parameterization to describe it. So this t also between 0 and 1, but now when t equals 0, and I'm here, and then going back to this point. Okay, so this is yeah. So if you already know parameterization for the curve C, and this is a C, okay, this curve C with orientation. And then you can use that parameterization to parameterize the same curve with the opposite orientation, okay, which is denoted by negative C, okay? So you can see that when t equals 0, this is a starting point, here's the ending point. And this is a starting point, this is the ending point, okay? All right. So we have the following important fact for it's a line integral. This is a line integral, and the f dot t ds. Okay, and this is going to be the integral. Yeah, if we reverse the orientation, okay, this will be c f dot ds and negative sign. Okay. So how do I see that? Okay, T is going to be the vector field, the same vector field F, right? F, yeah. Right, and in this case, T is tangent vector to the curve, and in the same direction as the orientation of the curve. And here, T is in that direction. Okay. All right, let's verify this important property. Okay. Okay, use the above parameterization. This negative c t f ds, right, is going to be integral from 0 to 1 f and bar t, and this is going to be this, right? Yeah, we just use yeah, those, so two different parameterization for the same curve but in different orientation. Okay, so this is going to be f r here, 1 minus t, right? When I differentiate, I get r prime, 1 minus t, but there is a negative sign, right? Okay. So now I'm going to use a substitution, let s to be 1 minus t, okay? So when t equals 0, s is 1. So this integral becomes 1 and 0. F r s, right? And r prime s, and negative 1, ds dt ds, okay? Right? dt is going to be negative ds. Okay, I have a negative, negative becomes positive. Okay, but the interval here is from 1 to 0. So if I change it, I get a negative sign. Now, this is nothing but the line integral from the line integral, the first one, from this point to that point, C, orientation from left to the right. Okay, so this is going to be denoted by negative C F dot T ds. Okay, okay, this is T. Yeah, sorry, this ds is yeah, this is a. So I use a T, I use a S here. Maybe I should use a tau. So then it'd be not confused with arc length. That's okay now. Okay, so this is a, yeah, if I use a tau, then that's much easier to understand. Yeah, let me change these variables. Okay, so let's use a tau, okay? And this is going to be, yeah, it's going to be tau. It's tau and the d tau, okay? Yeah. Okay, so that will be tau, tau and d tau. Okay. This is going to be tau, tau. Okay, yeah. Okay, this will be TDS. Then I'm not going to confuse with the letters. Okay, okay. So variables. So DS usually means the arc length of the curve. Okay, so we got this. Okay. Now I'm going to talk about in a line integral along closed curve. Okay, so we yeah, let's see be a simple closed curve. Okay, and D the region enclosed by C. Okay. Now this C also is oriented. Okay, so here's this is a curve C. C. It's a counterclockwise orientation. Simple means no holes in D. Okay, so that means this whole region there's no hole here. Okay. Okay. What is the example with the hole? For example, here's a region. This is going to be a region. This is not simple. Okay, clear, right? It's a closed curve, so the line integral sometimes we just can put a yeah. So now a vector field defined on D. Okay, so this is a F. The Greens theorem says that, yeah. So this is going to be P and Q have two components, right? The Greens theorem says that this line integral f t ds, okay, which if you parameterize by r, right, r t, then this is also denoted by f dr, okay? But now, yeah, now it is if you know the component p and q, okay, so this is also denoted by p dx, q dy, okay? So this line integral can be can be changed to the double integral. Okay. Well, this is an interesting result. Okay, you can in other words, the line integral around this curve C is going to be the double integral of this function. Okay. Okay, so let's understand this theorem. Okay. So from this theorem, we can see that if so my conclusion is, okay, from this theorem we here's a conclusion. You can get the following we call corollary. Okay, if f is conservative, okay, that means f is conservative. No, we don't need to say that. So if we have the following property, okay, then this line integral is going to be 0. Okay, right? So the integral along the curve, along the simple curve is 0. Now let's look at this again. So you can also get the following conclusion. Okay, so if you draw okay, so let's consider domain D. Okay, right, and take a 2 arbitrary point. So you have one curve C1 and another curve C2. Okay. Now, not in the same direction. But these two curves form a closed loop. The C will be from here to here, right? So that's called the C. So C actually consists of C2 and negative C1. Negative C1 reverse order, right? So according to, so if you have this, okay, then you can see that the integral of C, right, and p dx plus q dy equals 0, right? Right. But this one consists of two parts. It's going to be C2 px dx q dy, and then plus another one C1, negative C1 px q dy, okay? And this is supposed to be 0. But you know that this is still C2, okay, integral on C2. But this becomes negative the integral on C1 px q dy, okay? We already proved that. So that is going to be 0, right? It's going to be 0. So that means this line integral is going to be this line integral. Okay. So let me summarize that. Okay. Okay. So here's a theorem. Okay, we conclude it. Okay. So if if px dy, this is a qa. Okay, that's what's the condition. Yeah. If this is holds in D and C1 and C2 form a simple closed curve, okay? But they are starting from, okay, so same curves. Then this two line integral has the same value. Okay, so this is our corollary from Greens Theorem. All right, but the Greens Theorem is, yeah, from here you can prove that, then you can prove that for a simple domain, okay, that means no hole. If the above equation holds, then F is conservative. You can use that, okay? So then you can prove F is conservative. So by the above result, one can show that, okay, if partial derivative P with respect to X equals partial derivative P with respect to Y holds in a simple domain D, then F EQ is conservative. You can use a line integral to construct is conservative in D, i.e. F is going to be the gradient of some function for some F. Now how to construct F? Use a line integral. But you have to prove that the line integral is independent choice of particular curve. Okay, so the construction is simple. And how to construct this? This is a D, and fix a point. Remember, right? And here's the arbitrary point. Then you can take a curve C, and my F X Y is going to be some constant K plus the line integral Px plus Qy. Okay, dy. Okay, but you can say that this is independent choice of the C. Okay, from the fixed point, this is a fixed. This is an arbitrary point. So this is constant K. Okay, so you have to show that this is independent choice of a particular curve from the fixed point to then that given point. Okay, so this is how they construct. Okay, that's a proof. But now our today's main focus is for vector fields which are not conservative. Okay, and let's do the following example. Okay, example. Evaluate this line integral where C is a triangle with vertices, okay, 0, 0, 1, 0, 1, 2, with positive orientation. Okay. So positive orientation means counterclockwise. As this is a 0, 0, and the 1, 0, and the 1, 2. So it's going like that, okay? Now, if you're given the line integral like this, it's closed curve. Be careful. When it's closed curve, you have two options. Either you parameterize the three pieces, and then you use a line integral formula for the integral formula for line integrals. Then you can evaluate. Now we can use the Greens theory. Okay, this is a simple curve because inside there is no hole here, right? The function is defined everywhere. Okay, so the function is defined everywhere. So this is my P, that is a Q. Okay, so then you can say that by Greens theorem, okay, this line integral is going to be the double integral. That's a D, and here's the derivative of Q with respect to X minus the derivative of P with respect to y and dA. Okay, so let's simplify it. It's 2xy cubed minus just x. Okay, when differentiate xy with respect to y, it's get x and dA. Okay, so that's it. So now this is a double integral over the triangle. So you know how to evaluate, right? You can use the iterative integral. Okay, some students still don't know how to do that, and pay attention. So use okay. So use the vertical lines to fill the region. So then x is from 0 to 1. So x from 0 to 1, and put the x outside. Then for each x, you have to look at the y value. Okay. For each x, you have to figure out the y value. Y value is from 0 to something depends on y. Because the equation of this line is y equals 2x. I believe that. Okay. So the slope is 2. Yeah, it's passing through the origin. So the y value, the upper bound for y value is 2x. Okay, then this will be dy. So txy cubed x and dy. Okay, so now you evaluate this iterative integral. Okay, so inside here, be careful. X is a constant. Y is going to be the variable, so I have to divide by 4 minus x times y. Evaluate the two endpoints. Okay, so you plug 2x for y. I get 1/2 x, 2x to the 4th power minus 2x squared. Okay. But I'm going to simplify this again. 2 to the 4th power is going to be 16. Divided by 2 is 8. X to the 5th minus 2x squared. And then you find the entire derivative of this function. It's going to be 8 over 6 minus 2 over 3. X to the 6, x cubed from 0 to 1. Right? So it's going to be, that's 4 over 3, right? Minus 2 over 3. And after combine these two terms, you get 2 over 3. So you can use double integral to evaluate the line integral along a closed curve. Okay. So let's try another problem. Okay. Evaluate this integral c and here y cubed dx minus x cubed dy. Okay, c is a positively oriented circle of a radius 2 centered at the origin. Okay, c is positively oriented circle of radius I equals 2 centered at the origin. Okay. So we are, this is a circle. Let's see. Okay. Radius R equals what? Equals 2. So you can have two options. Now, if you use the line formula for the line integrals, parameterize a circle, and you will see it's pretty complicated. Okay, so let's set up this integral. Why not, right? So you let x to be 2 cosine t, y equals 2 sine t, t between 0 and 2 pi. Then dx will be, then this line integral, right, is going to integral from 0 to 2 pi, and the y cubed x prime, right, and x cubed y prime, then dt, right? because dx is x prime dt. Okay, so you have y cubed, so 2 sine t cubed, and the x prime is negative 2 sine t minus s cubed 2 cosine t, and that is going to be y prime is 2 cosine t dt. Okay, so after simplifying, what do you get? You have a negative, right? Negative 2 to the fourth power sine to the 4t minus cosine fourth power. You see, now you have to evaluate those two integrals. Okay, you have to evaluate those two integrals. And this is plus, okay, otherwise it's gonna be 0. But this is it's complicated, right? So question, yeah, then you have to deal with this integral of sine to the fourth power. Okay, so that's not a good idea. Now, but if you use Greens theorem, right, you will get by Greens theorem, okay, you will get double integral of d. Okay, d is the region included by the circle, so that's a d. Okay, and then the partial derivative of the q minus the partial derivative of the p with respect to y and the dA. Okay, so after you simplify, you get negative 3x squared, negative 3y squared, and dA. Okay, this is a perfect integral. It's great. You know, you can take a negative 3 out, x squared plus y squared dA. And since d is a circle disk, right, you can use polar coordinates. By polar coordinates, right, you get I is from 0 to 2 pi, and say that's from 0 to 2 pi, I is from 0 to 2, because this is a radius 2, right? And here's r squared, and r and d r d theta, right? So we can easily solve the problem. Okay, so this is going to be r cubed. R cubed is going to be 1/4 r to the fourth power from 0 to 2 d theta. Okay, r cubed, the antiderivative r cubed is r to the fourth divided by 4, right? So it's going to be 2 to the fourth power divided by 4 and d theta. Okay, that is going to be 4, right? It's going to be a negative 12. So negative 24 pi. Yeah, negative 24 pi. So that's great. So you can easily evaluate. So for integrals around the curve, closed curve, you can use around closed curve, but this is a simple closed curve, then you can use a Greens theorem. So now I'm going to generalize the Greens theorem a little bit. Okay, suppose there is a hole. Suppose, yeah. Suppose that C is not simple, okay? Which means, for example, this is a C, okay? It's not simple means there's inside, yeah. In other words, the region D is not a simply connect, okay? So that means there's a hole here, okay? So i.e. there's the region D enclosed by C, yeah, there's a, yeah, has a hole, okay? For example, so I'm going to C consists of two pieces actually. So this is a clockwise rotation, such like that. Okay. So this is a C. All right. So how can I set up an integral for this? So there's a hole here. Okay. It's right. So this is a domain. Yeah, so this is a D. So there is a hole here, okay? So then the D, this domain D is a hole there, okay? Now the curve actually have two pieces. That's going to be C1, maybe that's called C2. This notation means the boundary, okay? So this consists of C1 and C2, okay? So this is the boundary of the D, okay? Consists of two curves. Okay. Yeah. My question is, do we still have, this is do we still have px and q dy, okay, around this C, okay? So this is also denoted C, okay? C consists of two curves, but the opposite orientation, okay? The reason is, if you think about, at every point you look at like this, right? So on this side is counterclockwise, on the other side will be clockwise. You see? Right. Counterclockwise, right? On this side, and this side, lower side is clockwise. That's the reason rotations are opposite. All right. So this curve, does it still equal to the double integral of the function? Okay, and the D is that region was the hole there. Okay. The answer is yes. The question is, how do you prove it? Why is this still true? Okay. The idea is very simple. To prove that, you divide this region into two parts, cut it, right? So this is called the D1, that's called the D2. All right, so D1, the double, let's go backward, okay? So the double integral D can be divided into two double integrals. Right? One is on the D1, other one is on D2. Okay. But each double integral, look at this. Each double integral, let me draw this picture again. Right? Here's a cut it, right? Yeah. So that's a D1, that's a D2. So what I'm going to do is, for D1, it's a simply connected. So this is going to be the integral from here. You can consider these pieces. Right? And another one will be going this way. right? So I can apply the Greens theorem to the both regions. Okay, the Greens theorem to both regions. Let's look at the first one. According to the first one, yeah, I'm going to call it. That will be. Okay. So we already. Yeah, we already denote this is yeah, this is our notation. This is a curve C1. That's a curve C2. It's the inside one, right? It's a clockwise, and the outside is counterclockwise. You can see that why inside one has to be counterclockwise, because when you look at D1, when you go in counterclockwise, then here must be, you see they match the same direction, right? So this is going to be the integral, according to Greens theorem, is going to be the line integral. I'm going to denote this curve. I'm not going to use C1 because C1 is already used, right? So that will be, let's use a different notation for the closed curve in red color, okay? I called, yeah, just call it red color, okay? Red, okay? So that is going to be P dx plus Q dy, okay? And then, and this will be, I called rho, okay? So that's going to be the integral rho px plus Q dy. So those line integral, okay, and combine them together, and you will see that these two pieces here, they're opposite direction, that cancel out. So yeah, these two pieces cancel out, right? Because they're opposite direction. One is going this way, the one going that way. So after you combine them, you get the double integral of this plus C2 px plus q dy, okay? So then you group them together, is going to be just a C px plus q dy, because C is going to be the union of these two curves. But then we still have the Greens theorem for the domain, okay? For an arbitrary domain. Clear now? Not necessarily for simple domain. For an arbitrary domain, you have to make sure how many holes there, you know, then the boundary of the domain is going to be probably consists of many closed curves. So in general, we have the following theorem. Here's a domain D, and inside there are many holes here, right? Many holes here, right? So I can draw a picture, funny picture here. Okay, so the many holes here. All right. So now this is a D. Okay, this is a D. Yeah, this is the domain D. And this is domain D. The boundary of the domain D consists of how many curves? 1, 2, 3. Consists of 4 closed curves with orientation. With orientation. The orientation depends. So the most outside one is counterclockwise. Those inside are clockwise. Okay. With orientation, with certain orientation. Okay, I'm not going to specify that. It's clear, right? Then we have the following theorem. The line, the double integral over D. Okay, is going to be the line integral. okay, and the P dx plus Q dy, okay. In general, we have the following Greens theorem. Okay. So what is unchanged is just D, but the boundary of D consists of 3 closed curves. Right? So now let's look at the following case. Right. So in particular, okay, if you can have P and Q satisfy this equation, then this double integral is just the area of the function, just the area of the domain D, right? And this area of domain D can be given by this line integral. So remember, when we evaluate the line integrals along closed curve, we change it to the double integral. Now this time we're going to change the double integral to the line integral. Okay. So so what kind of function P and Q, or what kind of vector field satisfies the above equation? There are multiple choices. And there are multiple choices. For example, yeah, the set 1, right? And P is going to be Q is going to be X. P is going to be 0. How about this? Yeah, right? Or Q is 0. P is going to be -1. Right? Or P is going to be half of X. Half of negative half of Y. Q is going to be half of X, PQ, right? I can write on Q first, PQ, doesn't matter. Okay, all of them satisfy the above equation, okay? They are that satisfies this equation. You can check that, right? All right, what does that mean? According to above theorem, the area of the domain D can be evaluated along this its boundary. When P equals 0, when P equals 0, Q equals X, that'll be like this, okay? Or the second choice, P is -Y, so dx. Or you can use the last choice, half of -y dx plus x dy. Okay, that's Q is X. Okay, so you can use any of these line integrals to find the area. That's interesting. So the line integral gives you the area of the region. Okay, the line integral along its boundary. Okay, the line integral around the boundary gives the area of the region enclosed by this curve. This is amazing, right? So the information around the boundary gives the information of the interior part. Okay. All right. So let's take a look at the following example. Okay. Let's take a look at the following example. Find the area of the region enclosed by this equation. Okay, this is elliptical region, right? Okay, I want to find the area of that region. All right, so what is it? What is the way to do, right? The area is going to be, this is going to be double integral. Then you have to find, right? Find how do you do that, right? So the area is going to be the double integral dA. And how do you evaluate this double integral? It's pretty complicated, right? So now, according to the above theorem, it's going to be the line integral. Okay, it is going to be the line integral. Okay, and this partial d is just counterclockwise elliptic. Okay, so you can choose any of them. I'm going to choose. I'm not going to use a 2. Just use the first one, x dy. Okay, let's try to see. This is simple. Okay, so you have to parameterize that. X equals a cosine t, y equals b sine t. T is between 0 and 2 pi, right? 0 and 2 pi. Okay, so now it's going to be integral from 0 to 2 pi. X is what? A cosine t, right? Dy is going to be b cosine t dt. When you differentiate dy, you can when you, dy is going to be y prime dt, right? So dy is going to be y prime dt. All right, this is a simple integral. It's going to be ab, the integral from 0 to 2 pi cosine square t dt. And how to evaluate? Use the integral formula, right? Use a trigonometric function formula. It's going to be 1 plus cosine 2t over 2, and then dt, right? All right, but the integral cosine 2t is going to be, I take a 2 out. So this is going to be t plus sine 2t over 2, and evaluate at 2 endpoints. So sine 2t at the 2 endpoints will be 0. So what you get is ab over 2 and then 2 pi. So it's going to be ab pi. So this is the area of an ellipse. Okay, got it? So it's very easy to find the areas of the region enclosed by an elliptic curve around the origin. Okay, we use the the area is given by the double integral. Then change it to the line integral. Okay, then you have to parameterize the boundary of the region. Then you get this. Okay. Okay, so this section is mainly about the line integrals around closed curve or line integral around the boundary of a region. Okay, the boundary of the region depends on region. If the region has a holes, then boundary region consists of several closed curves with a certain orientation. If the region is simple, there's no hole, then the boundary has only one. The boundary has only one closed curve. Okay, so the region, yeah. So this is the region D, no holes. Okay, simple case, and then then this will be the boundary. Okay, curve. Then let me repeat again. If it has one hole there, okay, then this is not simple region. Okay, and D. Okay, then the boundary consists of two curves. That's the C2, that's C1, C1 and C2. The union of these two curves. Okay, and this is just a C, and that's just only C1. There's only one curve. Let's see what you see. Okay, so more general, if you have 1, 2, 3, and like that, right? Then this is a D, and there's a 3 holes here, and then you have a C1, C2, C3, C4. Okay, then the boundary of D will be C1, union of C2, C3, and C4. Okay, so that is then we always have the Greens theorem in this most general form. It says that the double integral of D is going to be the line integral, right? P dx plus Q dy, right? And doesn't matter how many holes there, okay? And if there's no holes there, and then just only one single simple closed curve, okay? And this theorem is used to prove to show that when the vector field is conservative, okay? If the domain there's no hole, then the line integral will be, the most important application of this theorem is if inside the D, if the D has no hole, okay, then if this P is part of the QXPY, the difference is 0, then the vector field is conservative, okay? So you can show that the vector field is conservative. And this is the most important application, okay? The most important application is, let me repeat again, is that if D is simple and this holds, then FPQ can be written as the gradient of some function. Okay, so i.e. f is conservative. Okay, but if when f is written in that form, gradient of some function, then definitely the above equation holds. Okay, you don't need to mention whether these are simple or not. Okay, if it is not simple, you cannot find single function together. Okay, you cannot find a single function. Yeah, there was a issue. Yeah, if D is not simple, then what happens? If D is not simple, okay, let's look at, for example, right? This is a D. It's not simple, so I'm going to cut into two here's D1, D2, right? I assume that you have this hold. So what I get, this side is simple, other side is simple, right? So this is simple, and this is also simple, right? So on this side, di on each side, you still can have, yeah, the vector field the same, right? P and the Q, you still have this, two functions, okay? So, but you have two functions here. Here's F2, here's F1, but we don't know how to glue them together, okay? In general, yeah, in general, F1, F2 are not differed by constant in general, okay? F1 minus F2 along this common boundary, okay? Along this common boundary, I call it, they're not going to be constant on this common boundary. How common boundary is the intersection of these two. So you cannot glue them together to form a single function, f. Okay. Yes, f is conservative on the left, f is conservative on the right side. Okay. But f is not conservative on the whole domain D if the domain D is not simple. Well, sometimes still yes, but I cannot prove that. Okay. There are examples you cannot. Yeah, exact examples. Those two functions you find out that do not match along this. Yeah, you cannot group them together along this common boundary. Okay, common boundary. If they only differ by constant, I can add one constant to another function. Then they're equal. Then okay, I have a whole function. Okay, so so we stop here. We're not going to spend much time to dig into this part.